plates sensibly. Okay, and using this kind of an arrangement, you can get an effectiveness as high as 80%. Even though you may be surprised that we use plastic materials, plastic tubes or plastic plates in a heat exchanger, because as you know, plastic has low thermal conductivity. Still, you manage to get high effectiveness because you get very high heat transfer coefficients outside the tube, because outside the tube you have latent heat transfer. Okay. So, since latent heat transfer provides high heat transfer coefficient, you get very large convective heat transfer coefficient on the outside, and this more than makes up for the low thermal conductivity of the tube material or plate material. Okay. As a result, you get very good effectiveness for with this kind of evaporative coolers. Okay. And plastic is also cheaper and it is also easier to manufacture. Now, several modifications are possible which improve efficiency of the evaporative cooling systems significantly. Okay, so let us look at what are these modifications. I will just discuss one or two modifications. One simple modification is that you can sensibly cool the outdoor air before sending it to the evaporative cooler by exchanging heat with the exhaust air from the conditioned space. So, this is one of the simple improvements. So, let me explain this. Remember that this is the air in a normal simple system. You are throwing this exhaust air into the atmosphere, and this exhaust air is at a temperature equal to that of the conditioned space. Okay, conditioned space temperature is Ti, let us say, and we know that the conditioned space temperature Ti is less than To. Okay, that means the temperature of the air at this point will be less than the outdoor air. Okay, so what you can do is you can exchange heat between these two. For example, if I put a heat exchanger here, okay, so this air flows through this like this, and this primary air before sending it to the air washer flows through this, let us say it flows like this. So, as a result what happens, the temperature of the outdoor air gets reduced as it exchanges heat with the exhaust air. So, what enters the evaporative cooler is a cooled air. That means instead of entering at this point, this will be sensibly cooled by exchanging heat, and at this point cooling and dehumidification takes place. So, you can see that you can achieve lower temperatures by using this simple modification. Of course, achieving good heat exchanger effectiveness using air to air kind of a heat exchanger is very difficult, because you have to have large surface area, etc. That means you have to use a compact heat exchanger if you want to have good effectiveness. Okay, so you have to see the benefit versus the cost involved. Okay, but in principle this is a simple modification which can give a certain improvement. One can also use multi-stage systems, and using multi-stage systems it is possible to cool the air to a temperature that is several degrees lower than the wet bulb temperature of incoming air. So, this is an advantage of multi-stage systems. So, let me explain a very simple multi-stage system. Okay, so this shows a simple a two-stage direct indirect evaporative cooling system. Again we have a primary air stream here and a secondary air stream here. So, in the first stage what happens is the primary air stream is cooled and humidified in the evaporative cooler, okay, like we have discussed earlier, evaporative cooler. So, it gets cooled and humidified, then this cooled and humidified air flows through an air to air heat exchanger, okay, air to air heat exchanger, where it exchanges sensible heat with the secondary air. Okay. So, up to this point it is exactly similar to an indirect evaporative cooler. So, what you get out of this first stage is cold air, okay, whose humidity is same as the outdoor air humidity, right. So, its temperature reduces, but humidity remains constant. Now, in the second stage, this point onward, this is the second stage. In the second stage what happens is this secondary air undergoes direct cooling and humidification in a second evaporative cooler. This is your second evaporative cooler. Okay. So, in the first stage only primary air gets cooled and humidified, and secondary air exchanges sensible heat, whereas in the second stage the secondary air undergoes cooling and humidification. So, as a result what you get out of this, that means at the final exit of the system you get air which is much cooler than the incoming wet bulb temperature. In okay, wet bulb temperature the incoming air. The same thing is shown here on the psychrometric chart. For example, this is the condition of the secondary air here and the primary air here. Okay, so the primary air undergoes cooling and humidification. So, O dash is the exit of the first evaporative cooler, and at this point this flows through the air to air heat exchanger, so its temperature increases and the temperature of the secondary air reduces in this direction. Okay. So, at the end of this, okay, point 1 is here. So, at this point it enters into the second evaporative cooler, okay, where it undergoes cooling and humidification. So, finally, what leaves this complete unit is air in an ideal case, which is at a temperature T2. Okay, so, this is the final temperature of air from this system. Now, you can see that this temperature T2 is much lower than the wet bulb temperature corresponding to the inlet air, that is nothing but this. Okay, that this is the wet bulb temperature corresponding to outdoor condition, and this is your exit temperature Ts. So, you can see that Ts is lower than T wet bulb temperature. Okay. So, this is a simple two stage system. One can also think of other schemes. Okay, one can also go for 3 stage, right, 3 stage direct, indirect, direct, direct, indirect, like that several schemes are possible. So, using these multi stage schemes, you can achieve temperatures which are much lower than the wet bulb temperature of the incoming air. But of course, the disadvantage of these kind of systems are the cost increases because you are adding more and more components. Okay, so, the initial cost of the system increases and the running cost also increases because you have several pumps and blowers, etc. All these components require some power. Okay, so, both running as well as initial cost increase, and the benefit you get is you get air which is at much lower temperature. So, you have to again see which is beneficial, right. One thing I forgot to mention is the use of this pump. Okay. So, we have to use a water pump in an evaporative cooler because in a typical evaporative cooler you have to maintain these wetted surfaces continuously wet. Okay, these are the wetted surfaces which have to remain wet continuously. So, what you have here is a pool of water. Okay, a pool of water. This pool of water, the pump is connected to this pool of water. So, it continuously draws water from this pool and it pumps it to the top of the evaporative air cooler and it throws it onto the wetted pads. Or if it is an air washer, then it sprays the water droplets into the air washer. Okay. So, the pump is required for the continuous circulation of the water, whereas the blower is required for, I am sorry, a blower is required here for circulation of air. Okay. So, these are some improvements using which you can extend the application of evaporative coolers. Now, let us look at the advantages and disadvantages of evaporative coolers. What are the advantages? First advantage of course is that they have a lower equipment cost and installation cost compared to the conventional refrigeration system based air conditioning systems. Okay, the equipment and installation costs can be several times lower than the conventional systems. And they also have substantially lower operating and power costs because all that you require is power for running the blower and for pump. You do not have a compressor there, so the power consumption is reduced substantially, and the energy savings can be as high as 75% compared to a conventional air conditioning system. This is a major advantage of evaporative cooling systems. And of course, the third advantage is that it is very easy to fabricate these systems and it is also easy to install. The fabrication is so easy that it is like a cottage industry or like a small scale industry, and in several places in India very small industries manufacture these evaporative coolers. So, as a result they are available at a much lower rate. Okay. Whereas the conventional systems not everybody can manufacture them because the manufacture of compressor and all is a very expensive business. So, fabrication is also difficult there, whereas evaporative coolers can be fabricated very easily, and the installation is also very easy. For example, if you are using it for cooling a room, you do not require any installation at all that you have to do is buy it, bring it and plug it in. Okay. So, it is as simple as that, but if you want to use a conventional air conditioning system, then you have to install the system, you have to create air ducts, etc. Okay. And the lower maintenance cost, since you do not have any compressor, the maintenance cost is considerably reduced. So, this is another advantage, and these systems ensure very good ventilation. This is because as I have already mentioned, the required air flow rates are very large in these systems, and typically in these systems you do not recirculate the air. So, whereas in a conventional system you recirculate the air, but whereas in an evaporative system you exhaust the air. Okay. So, you continuously draw fresh air, cool and humidify it and supply it to the conditioned space. Okay, so not much of recirculation is used. Recirculation is not very effective also. So as a result, a continuous supply of large amount of fresh air is ensured whenever you are using evaporative cooler. So this will take care of ventilation. Okay, so this is another major advantage. So because of the large flow rates involved, the conditioned space air distribution is also ensured. That means you get better conditioned space air distribution because of the large amount of air flow rates involved. And there are no infiltration losses because the air flow rate is very high. So normally you find that whenever you are conditioning a building using evaporative cooling system, the pressure inside the building will be positive. That means the pressure inside will be higher than the outside pressure. So as a result, if there is any leakage, it will be a leakage of air from the inside to the outside, not the other way. Okay, that means there won't be any infiltration of outdoor air into the system, into the conditioned space. So there are no infiltration losses, right? And last but not least, these systems are environment friendly. These systems are environment friendly because we do not use any chlorofluorocarbons or any harmful chemicals, etc. in these systems. So all that we use is air and water. Okay, so they are very environment friendly systems. Okay, so over and above that, since they consume less power, obviously they also lead to lower global warming potential. Okay. However, these systems obviously have some disadvantages. What are the disadvantages of these systems? First disadvantage is that higher moisture levels in the conditioned space, because the air that you supply to the room is at a much higher humidity ratio. So the moisture levels in the conditioned space will be higher, and these systems may create draft or high noise levels in the conditioned space due to large airflow rates involved. Okay, since you have to deal with large airflow rate inside the fan, may create a large noise. Okay, if the flow rate is also high, you will also have you may also have the feeling of draft. This could be a disadvantage from the comfort point of view. And another disadvantage with these systems is that precise control of temperature and humidity in the conditioned space is not possible. Whereas using a conventional system, you can precisely control the temperature and humidity inside the conditioned space. And fourth disadvantage is that these systems may lead to health problems due to microorganisms if the water used is not clean or the wetted surface are not maintained properly. Okay, so if you use a dirty water or if you don't clean the evaporative coolers from time to time, then fungus or algae or something may form inside the evaporative cooler or on the wetted surfaces, which may give rise to growth of microorganisms. And since the air blows over it and you inhale that air, this air may give rise to health hazards. Okay, so you have to maintain it properly so that no fungus formation or no microorganism formation take place. Okay. Now let us look at the applicability of evaporative cooling systems. I have mentioned that one of the disadvantages or one of the limitations of evaporative air cooling system is that as the outdoor air humidity increases, the required mass flow rate of air increases, and beyond a certain humidity ratio you cannot use evaporative cooling systems. Okay, that means you can use them beneficially in certain locations and you cannot use them in certain locations. So how do we decide where these systems can be used or where these systems cannot be used? What are the guidelines? Okay, so let us look at these guidelines. It is observed that these systems can provide some measure of comfort in any location. Okay. However, when humidity levels are very high, evaporative cooling systems cannot be used for providing thermal comfort, especially in residences, office buildings, etc. In residences and office buildings, etc., providing thermal comfort at the required level, that means maintaining the conditioned space at the required level, is very important. Okay, that is the primary job of any air conditioning system. Okay, if the outside humidity ratio is very high or the outside air is very moist, then we have seen that these systems, that means the evaporative air cooling systems, cannot provide the required levels of comfort. That means you cannot use them for comfort applications where the outdoor air is very moist or very humid. Okay. So what are the useful guidelines? These guidelines are not very stringent, but they just give some idea on where you can use or where you cannot use. Okay. So one older guideline is that evaporative cooling should be considered as a viable alternative in locations where the average known relative humidity in July is less than 40%. Okay, that means if the relative humidity at noon during the month of July, average relative humidity during the month of July at noon, if it is less than 40%, then you can definitely use evaporative coolers, and you must consider evaporative coolers as a viable alternative to the more expensive conventional air conditioning systems. Okay. However, it is seen that you can also use evaporative coolers in areas where the known relative humidity is slightly higher than 40%. Okay. So, that means this is a very stringent guideline. So, there is another broader guideline which says that evaporative coolers can be used in places where the design wet bulb temperature in summer is less than about 24 degrees centigrade or about 75 degrees Fahrenheit. Okay, that means if you know the design wet bulb temperature during summer, and if you know that it is less than about 24 degrees centigrade, then again you can consider the use of evaporative coolers. Okay, these guidelines are obtained mainly for single stage direct evaporative coolers, and indirect evaporative coolers and multi-stage coolers can be used over a broader range. Okay, that means you cannot simply say that evaporative coolers cannot be used in particular location. Okay, you cannot use a simple direct evaporative cooler in certain locations, but if you make modifications, if you use a multi-stage system, you can extend the range of application of these systems. Okay, to even humid areas. And these systems are highly suitable in applications requiring large amounts of ventilation. Okay, there are many applications such as textile mills, foundries, dry cleaning plants, etc., which require large amount of ventilation, and here you cannot provide full comfort, but even if you can provide a partial comfort, that is more than welcome. So, in such situations you can think of using evaporative coolers, which will give you a very cost effective solution. Okay. And evaporative coolers can be combined with conventional systems, leading to lower total energy consumption. That means you can also think of hybrid systems which use a combination of evaporative cooling systems and a conventional air conditioning systems. Okay, using a combination of these two, you can arrive at lower energy consumption. Okay, so one simple scheme is that the outdoor air is first cooled in an evaporative cooler. Then you send that cooled air, which is not cooled to the required extent, but which it is cooled to certain extent. That cold air is sent to the conventional air conditioning system, so that the load on the conventional air conditioning system reduces. Okay, so which will give rise to savings in energy, right. So, there are a lot of possibilities where you can think of hybrid cycles. Okay. So, as far as possible, looking at the geographic locations and looking at the climatic conditions, one must see first of all whether one can use evaporative coolers or not. If we can use evaporative coolers, then you should definitely use it, because it is having many advantages and it gives rise to many benefits, both as in terms of initial cost as well as in terms of running cost. Okay. And however, there are certain applications, as I have already mentioned, where you cannot use them. Okay. In such cases you have to go for the conventional systems. Okay. Now, let us look at winter air conditioning systems. In winter, outside conditions are cold and dry. So, that means outside temperature will be very low and outside humidity will be very low. That means outside moisture content will be low. As a result, there will be continuous transfer of sensible heat as well as moisture from the buildings to the outside. That means the buildings continuously lose sensible and latent heat to the outside environment. So, in order to maintain required comfort conditions, air supply to the conditioned space should be heated and humidified. In summer, outside conditions are hot and humid. So, what you have to do is you have to supply air that is cold and dry. Okay, that means you have to generally supply cold and dehumidified air in a conventional system. Whereas in winter, it is exactly opposite. You have outside conditions which are cold and dry. Okay, so there will be heat losses from the building. So, to overcome the heat losses, you have to supply air which is hot and humid. Okay, that means basically you are looking for a heating and humidification process. Okay. And another difference between summer and winter is that in winter the heat losses from the conditioned space are partially offset by solar and internal heat gains. Okay, the solar energy actually adds heat to the building, and internal heat gains are also add heat to the building. So, that it partially offsets the heat losses from the building. So, in a conservative approach, what is done is these heat gains are not at all considered in the design. Okay, and you assume that there is no internal heat gain and there are no solar heat gains, and you arrive at the required system capacity. So, this is a conservative design approach as far as winter air conditioning systems are concerned. Now, heating and humidification of air can be achieved by different schemes. For example, you can use a preheater, a humidifier and a reheater. So, let me explain this system.